Welcome. Today we're going to be talking about a new kind of automata called an instantiating state automata, suggested to me by Christopher Nugent. And this is Dr. Perkins. As you know, having studied with this class, there is an existing abstract machine hierarchy that computer scientists and linguists deal with. Finite state automata by itself can express regular expressions. A push-down automata can recognize context-free grammars, and a Turing machine can recognize unrestricted grammars. The differences between these are pretty small. The difference between a finite state and a push-down automata is limited memory. Just a little bit of limited memory. You can't change the input. You can just save the output. A little bit of limited memory gives you the ability to match. Turing machines have write capabilities as well. So this is kind of a write. A push-down automata is writing to the stack, but it's a very restricted data structure, and it's only one data structure. So push-down automata have limited write memory. I guess I should change this here. And Turing machines have write capabilities that exceed the limited capabilities of a push-down automata. Now, the way Turing machines were posed, these write capabilities were the ability to change the input. I do not think that this is needed at all, this ability to change the input. But we do need these infinite tapes and the ability to write. These abstract machines were designed in the 60s and the 70s, although of course the Turing machine was earlier. And they were developed modeling the software that we were writing at that time. So the theory of computing was developing this abstract machine hierarchy a half a century ago when we were using programming languages like Fortran 66, Fortran 77, COBOL, which is even worse, Algol, which had some nicer features, Pascal. These are very simple languages. Moreover, they are not the type of programming languages we are using today. What do they have in common? None of them are object-oriented. None of them have selective inheritance. And those are the major features that we develop software with today. Object-oriented programming was introduced with the language Simula and then Smalltalk. Smalltalk was developed for Dynabook. And Smalltalk and Simula are pure object-oriented languages. Everything is an object. Alan Kay, very important name in computer science, who got his PhD from the University of Utah, worked on Simula, improved it, and brought it to Xerox PARC. At Xerox PARC, he continued work on Dynabook, written in Smalltalk, which is really an extension of Simula. Object-oriented programming was still kind of a side thing for computer science until Sundstrup developed his version of C++. So when they upgraded C, a language which we all knew, to C++, we just had to learn a few new features to be able to try to write object-oriented programming. We also had to change our way of thinking about code, and that took a little longer. C++ is a hybrid procedural and object-oriented programming, which allowed selected inheritance. It made efficient inheritance because it used static chaining as the default. Before C++, before object-oriented programming, computer scientists did not like static chaining. But all of our languages had it because dynamic chaining, which is sort of inheritance, you guys think of inheritance, dynamic chaining was too expensive. So by building this hybrid, C++ allowed us to be efficient most of the time and then do a little bit of dynamic chaining via inheritance through the objects only when we needed, making C++ still a reasonably fast language. As a point of interest and entertainment, a group at Mississippi State worked on object-oriented Fortran, just like Stroudstrup worked on his C++. A large group, 4 or 5 people, worked on OOP for Fortran for a decade. And when they finally got done, that they concluded that object-oriented programming looks the same as C++, which I thought was pretty cute. So, what does this mean in terms of these abstract machines? Because we can instantiate methods and data structures, programs no longer have a fixed number of states. I'm not just working with one subroutine. I can instantiate that subroutine 7 times and have copies of it. We are not using unrestricted state generation either, at least not right now. So we have a very limited type of state expansion in our codes, and that limited type is with OOP. It gives us a way to expand the number of states in a very controlled way. So the generated states are not unrestricted. They're via object definitions made specifically for instantiation following the C++ model. But our theory of computing structural hierarchy no longer represents this way of programming. It's antiquated. So according to Chris Nugent, it's time to update them, and it's a very fun thing to do. So I thought you would enjoy following an approach. So we're going to update our finite state automata to reflect the capabilities of current programming languages. And we're going to do that by following OOP, programming languages like C++. We're going to allow ourselves to instantiate a template pattern. And we're going to add inheritance. I'm not positive that we need this inheritance quite as much as we need this template pattern, but I think we need both. When we finish our abstract model, we'll again, like it did in the 60s, reflect existing programming practices. That will allow this model, even if it doesn't change the hierarchy, it will allow this model to better represent our algorithms and allow us to better study them in a more abstract way. So, enter the instantiating state automata. I just took off the second bullet point because it was for a different lecture I was working on. I was working on them at the same time, and I must have typed it in to this instead. So we're going to enter an instantiating state machine conceived by Chris Nugent because his fertile brain just works that way. We're going to have 2 levels of finite state automata. In our examples, I have no problems with the methods themselves instantiating more methods in a hierarchy of classes, but my example here will not describe that. It will describe only 2 levels. We will have a static finite state automata. It's kind of like your main program. and it will have templates for the dynamic finite state automata. No dynamic finite state automata will exist in the beginning, but they will be instantiated as needed. So, for example, I have my static finite state automata and my static OOP templates. And then, as I'm running this, I will instantiate these templates as needed, switch control down to these subroutines, and then return. My static finite state automata will be identical to the finite state automata used so far in class, but the notation will be different. Of course, we will think of it as a transition function that takes its current state and the current value on the input tape and either maps to a new state in this finite state automata and does not overwrite the input, but may or may not move left. I should actually write this. No, right. Apologize, I've been working on this for hours and still don't have it right. So I have my transition function, and it's going to take whatever state I'm in and whatever's on the input tape. It will either map to a new state on this static finite state automata, and the input tape will either move, I can write. It will either move right as it consumes input, or it will simply stay where it is. So it can either move or stay. It's not going to go to the left. I don't think we need that. Or it'll go to a QM, a new state, inside of something it instantiates. And it also can advance the input value or not. So this is on the finite state automata, and this is its state, and this is the state in the instantiated automata. So this either goes to a pretty standard transition function, the only difference being we'll specify that you don't have to always move immediately to the right, or it'll go to a state in an instantiated subroutine or method, and you can also move it. So let's look at these symbols. TV is the value on the input tape. Q sub j is your current state. QK is the next state if nothing is going to be instantiated. So if there's no instantiation here, this is the finite state automata. If there's an instantiation, this is the state in the instantiated device. Epsilon, which I took out, indicates that nothing will be instantiated. I was trying to make these look equivalent. That's why I put the epsilon there. Maybe I shouldn't have taken it out because I kind of like that. So I'll stick it back in there. Epsilon. So epsilon indicates that nothing will be instantiated or something will be instantiated, and this is the class to instantiate. So we'll have K classes, M classes, whatever. Q to the M is the state within the instantiated class to enter. There will be more than one possible state for an instantiated class to start with. No offense, I wanted to save those changes.